Okay, but do you want to quickly introduce yourself and then let's just talk about your paper and
Yeah,
yeah.
of course. Thanks so much for having me. This is really cool to be here. And yeah, I can't promise you graphs, at least no message passing, I think. But there will be some geometry, like you said, and hopefully, if all goes well, also some learning. Um, yeah, my name is Johann. As Hannes already found out, I'm from Germany originally. I have a physics background, but at some point I transitioned into machine learning, like maybe a few of you. I did a postdoc with Kyle Cranmer, who many of you may know in New York, where we worked on machine learning for the physical sciences, in particular simulation-based inference. And then afterwards, I joined Qualcomm AI Research in Amsterdam, where I worked with Taco Cohen and Pim Dahan, and yeah, kind of the co-authors of this paper. So you see their names already on the slide. And we worked on different things, including some geometric deep learning. Maybe you know Taco also in this context. And this is our last project actually from that time. I've a few months ago I've joined Cusp AI in Amsterdam with Max Welling. We are a startup working on materials discovery, and that's also something I'd love to talk about at some point, but I don't have anything to show on that today. So I just have my last little bit of Qualcomm work here. And in the talk, I have a couple of slides that will definitely not fill an hour, so please interrupt me at any time. And I hope that's also what you usually do. And if I
Yes.
don't see your raised hand, I have it on a different screen here. I try to pay attention, but please just talk over me if I don't pay attention to any signaling. Um, and yeah, please make it interactive. Good, then let me just get started. Say you are one of the lucky ones. You have enough compute at your hands. You have lots of data for your problem, and you also know the symmetries of your problem. In this situation, maybe it's hypothetical, maybe it's real, should you bake the symmetries of the problem into your neural network through equivariances, or should you just use a kind of free-form general purpose neural network like a transformer or an MLP or whatever you want and learn the symmetries of the problem also from your data? This question has been discussed a little bit in the last year, and I think the debate was not very positive for team equivariance, mostly because some high-profile projects like AlphaFold 3 opted for non-equivariant architectures on very clearly symmetric problems. And another paper was something on conformer generation, a force field model. Force fields were always one of the strongholds of equivariance, but the orb model by orbital materials also opted for non-equivariant architecture. But at the same time, I think there's still some reason to think that equivariance is useful for something. And maybe my understanding of this, I'd summarize like learning always means you start with a big hypothesis class and you collect evidence to narrow down your hypothesis class. And if you start from a big hypothesis class of all functions or all smooth functions or something like that, like a transformer can represent them, it takes a lot of learning, a lot of steps of optimization to arrive at a narrow solution. And if you already know some symmetries, you can start from a smaller class of functions. And maybe then the narrowing down is more efficient and you arrive at a more precise solution with the same amount of compute. So that's, for me, the reason to think that equivariance may be great. And we try to study this question, should you make your networks equivariant if you have enough data, enough compute, a bit more concretely by asking three concrete questions, namely, how do equivariant and non-equivariant architectures scale as a function of the amount of training data you have? And how does data augmentation change this? Second, how do equivariant and non-equivariant architectures scale as a function of the amount of training compute you have? And are there universal scaling behaviors? Are there power laws or something like what people have observed in language modeling? Do the coefficients of these scaling laws change between equivariant and non-equivariant architectures? And finally, if you have a given compute budget, say a number of cloud credits at Google or something, and you want to get the best possible performance, how should you allocate your budget to the size of your model and for how long you train it? Now, that's where we want to go. How we address this is entirely empirically. We thought about some theory for this, but to be honest, I'm not really aware of any entirely convincing theoretical work on scaling behavior. There's some papers, but I think the community hasn't really fully embraced them. So we said, as long as there's no convincing theory of scaling, we stick with empiry. And we focused on a single benchmark problem. And in our benchmark problem, what we wanted to have is a problem that is where there's a big difference in the performance of a small model trained on little data and the performance you could achieve with lots of data and a big model. So low floor, high ceiling. We also wanted a problem that has clear true symmetries and one where we could generate enough data reasonably cheaply. What we ended up doing is focus on rigid body physics. So here, think of a number of 3D objects, all described as some kind of meshes that you throw together and that collide off each other. And that maybe also interact with gravity, and then they bounce off the floor a little bit and roll around. And the task is, given the current state and maybe the past state one time step ago, predict where everything will be in the future, in the next step. This is a difficult problem because the physics of these rigid body collisions is basically discontinuous. If you just change your orientations of the inputs a little bit, you'll get out quite drastically different behaviors. And machine learning algorithms have really struggled in learning rigid body physics. There's some nice work by DeepMind, where I also took our benchmarks that we used from them, but it's still far from solved. Concretely, what we do is we take scenes with something like 10 different objects. Each of them has something like thousands of mesh faces. So this is reasonably fine-grained. Each mesh face is a triangle. It has 3 vertices. And we describe all of these mesh faces as a sequence of tokens. So each mesh face is a token and has a couple of features that describe the positions and velocities of the edge points of the mesh face. And then we also have some auxiliary features like surface normals. It doesn't really matter for this talk. And as a metric, we use the error in predicting one time step into the future. And from this, you could also then, this is in a one-to-one relation with longer horizon predictions, but that's just more difficult because of chaos. Now, I think a very fair question here is why we chose this and not some more immediately relevant, let's say, chemistry or biology benchmark. And I think it was just very easy to generate data for this. We use a physics simulator called PyBullet. There's others out there as well. And it has all the right properties we want. And also, when we started out, we were kind of planning for this to be the first of multiple benchmark problems. And we didn't really get to the point before we all left Qualcomm, more or less, to have more benchmarks. So unfortunately, I have no, I don't know, interatomic potentials or something as an additional benchmark in here, but that would have been extremely interesting as well. Now, on this benchmark problem, we compare 2 architectures. A non-equivariant architecture and an equivariant architecture. And here with equivariant, what I mean is equivariant to E3, the symmetry group of translations, rotations, and mirrorings of the scene, which is most of the symmetry of this problem. There's also a permutation symmetry here between the different mesh faces. They don't really care about the order in which they are written down, but already a standard transformer is permutation equivariant. So both architectures have that. Now, I already said it, the kind of baseline model, the non-equivariant architecture we want to use is a transformer. And the reason for this is that we wanted to use an architecture that is known to have a great scaling behavior in many other fields, in vision and in language particularly. And we want to compare this standard non-equivariant transformer to an equivariant, E3 equivariant architecture that is as similar as possible to the transformer blueprint. And what we ended up choosing is entirely coincidentally our own architecture from a year ago, the geometric algebra transformer, or GATA. And this is basically a standard transformer that uses geometric algebra, which is a higher order extension of regular vector spaces. I think maybe you had Johannes Brehmer at some point in your reading group to talk about this, or David Ruber. I think I saw that on the schedule.
Yes, that happened a few times, and we're somewhat familiar with them. And if I'm talking already, I want to quickly ask, for all your simulation data that you obtain, do you always have the same bounciness parameters for your rigid objects, or how does this basically the elasticity of the objects work?
That is a great question. So each object is 100% rigid. There's no elasticity in them. But there's a couple of other parameters that we do change. So the mass of the objects, or the density, if you wish, is always different. So that's also a scalar parameter that we give as an input to the models. And the friction coefficient is different. And I think there was something else that I'm now forgetting. But they are not elastic. So elasticity would be an additional complexity that we left out.
Yeah, but so and all kinetic energy, or what is it called? A momentum is preserved and the stuff leaves with the same momentum as it comes in, or how does it go?
There's friction. So this
Ah,
is
yeah,
on the
yeah.
level of approximate Newtonian. I mean, it's the right physics at that length scale. So energy is not really preserved.
Okay.
So
Uh-huh.
something evaporates into heat and we don't see it.
Yeah. So the thing the model gets is a weight, and every vertex has the same weight parameter input to it. Like it's just one number per rigid object, and every vertex has a position and velocity.
That's correct, yes. And then there's a few derived features that didn't make a big difference, if I recall correctly, but we also give them the surface normal on each mesh face as an additional feature to the tokens.
Mm. I'm just concerned that it's like a um, right, this task or this information is very overrepresented. And now, or you could have a coarse-grained representation that perfectly captures this as well. And perfectly, yeah, you could have a coarse-grained representation that perfectly captures this as well just because you have a rigid object, and you could only be looking at one or two or three velocities, right?
Yeah, I mean, a rigid object is fully characterized by the momentum of its center of mass, or anywhere really, and the rotation around that,
And its
thermal
shape.
momentum around that.
You
Um,
also need its shape.
oh yeah, right. I mean, just the movement state is completely characterized by just a couple of numbers, so that's totally true. But then the interaction with other things will totally depend on the shape, and for that shape, you need all these mesh details really matter, right? Because you typically like some little corner of one object will hit.
Yes. But so
Yeah.
all the coordinates matter, but only three velocity vectors matter.
Per object.
Yeah. Right?
Yes, I mean up to you have this kind of rotating movement, this angular momentum as well, but then let it be, six numbers. But yes,
Okay. But if you
you have a
have
spinning
uh,
cube or something.
three velocity vectors, then doesn't that capture the velocity already? The angular momentum already?
Sorry, I thought you meant three components of one vector, but no, then I agree. Yes, yeah, that is true. But that alone, I mean, the challenging part in this is not really predicting linear movement, right? Like just kind of, having
Yeah.
a rotating cube in the air that accelerates under gravity. That's easy. The hard part is the collisions.
Yeah. Uh,
And it's
okay.
not also what we saw. Like you need very little training, and both models will learn that objects move on straight lines, and a little bit more training, and they learn acceleration by gravity, and a little bit more training, and they learn that they kind of stand still on the table at some point. But collisions are really difficult.
Yeah. I think we'll get into some more result discussions about that later on as well when we look at results. But let's continue.
Yes. But I think it's a fair question whether this particular benchmark captures properties that are important for other problems. And up to the fact that this is a difficult enough problem that models don't really saturate it, and it's equivariant quite clearly. Those two things I'm confident saying, and everything else is I don't want to speculate. Like maybe we find something here that really doesn't translate to, uh, you know, uh, biology or chemistry or whatever other applications you may have, and that's fair. That's what it is. Okay, back to the model. So we have this standard transformer and this geometric algebra equivariant transformer. Just to give you a very quick idea of what the characteristics of these two models are and how we use them on this problem. The inputs are kind of, as I've just said, are positions in the 3D space and velocities and a couple of slightly derived features from this. We tried just giving the numbers to the standard transformer. That worked okay, but we got a better performance if we use Fourier features to embed the 3D, I think both positions and velocities in addition to the standard thing. So this is, if you want even more over parameterization, but it really helps the transformer because then inner products between these Fourier features correspond to something like distances. So it's much easier for like a standard not geometric algebra-based transformer to figure out geometric features. And it's also pretty standard in machine learning, so we thought, why not give it a little bit of a leg up? The equivariant transformer has naturally the ability to represent geometric data in the geometric algebra. I see Steven in the room here, so we have an expert on this topic in the call. If you have questions, I don't have to answer them. The computation of these models, as you know, in a transformer is kind of split between the compute that happens within each token and the compute that happens between tokens. And this is very similar between the baseline and equivariant transformer. So the within token compute is an MLP, and the between token compute is dot product attention. And I think this is really the attractive property of this particular equivariant architecture, that is really just based on dot product attention, just with a slight modification to make it equivariant. But you can use the same efficient backends like flash attention, for instance. So it scales in terms of actual compute time, it scales reasonably well. More on this later. There's one small detail here. We use a hierarchical attention mechanism. It's really a small modification, but I haven't seen it anywhere else. So maybe you find this as a little trick also interesting. The idea here is the data in this particular problem is hierarchical, right? You have each token is a triangle. They are grouped together into objects, and the objects, multiple objects together form a scene. So there's kind of 3 levels of hierarchy. And we want to give the model a little bit of awareness of this structure. And the way that we do is that we split the attention heads in the transformers by letting some of the attention heads only attend within each object. So kind of one face can only attend to the other mesh faces that belong to the same object. And then other attention heads can attend to other objects as well. There's no particular logic for collision detection or anything here. You could do that, but we wanted to keep it as general purpose as possible. But I think this kind of 2-level hierarchy, encoding this in this way is super simple and has no real computational overhead. And then finally, the outputs of these models are a bunch of numbers for each token. But we have one last small modification here, or application, if you want. We enforce object rigidity. With that I mean is that each model outputs, let's say, an acceleration vector for each mesh phase, but then we aggregate them. We take the mean over each rigid object to make sure that they are accelerated in the same way. Well, accelerated and turned. There's both terms. Otherwise, the model could, in principle, let objects fly apart, and we don't want that. This doesn't really make a huge difference, but especially the standard transformer likes a little bit of inductive bias of this form, and it helps.
Okay, for the between token compute, the attention. So do you now have like just you take the tokens from every object and you concatenate them to each other and you throw them into your transformer? Or what, like how does this hierarchical thing work?
Yes, pretty much that. So in the way that it's kind of represented in a computer, it's really just a long sequence of tokens corresponding to all the objects and both time steps now and one step in the past. But then during attention, you can always supply to your attention operation these attention masks. And in particular, there's efficient implementation if you want to allow each token to only attend within a certain block to other tokens, so kind of blockwise diagonal attention masks. So what we do is that for some attention heads, you can basically attend to anything, any data, any mesh face of any other object. But for some other attention heads, we just allow them to attend to the part of the geometry that is rigidly connected to them, so the same object.
Makes sense.
Yeah, it's it's super simple. I've seen something similar in message passing before. So there were graph neural networks that had some kind of 2-level graph where sometimes the messages were just passed within each object and sometimes kind of with everything, kind of almost fully connected, except that wasn't.
And do your do you have positional encoding basically of saying which object you belong to?
No, because I thought about that and I couldn't think of a way that wouldn't break the permutation equivariance. Right? If for instance, if you do like a one-hot embedding of object number, then you have a number of problems. One is that you kind of lose this ability to scale to bigger scenes unlike the ones you've seen during training. Like you have a maximum number of objects in the scene, but also your network output will depend on which object number you have. So there's no, so positional embedding, of course, is a bit a tricky word, but there's no kind of representation of the position in the sequence anywhere.
But you already have that right via the attention. Like it's no longer permutation equivariant because you have this attention mask.
Great question. It is still permutation equivariant in the sense that if you totally reshuffle all your tokens, but also kind of keep track of which tokens belong to the same object and just
Right, right.
together, then it's still equivariant. There's no, like, it doesn't really matter which one you put first, which object.
Yes.
But
You will also be shuffling the mask.
yes, exactly. As long as you also shuffle the mask, it's equivariant.
Yeah.
But there's no kind of absolute representation. There's no notion that this is object one, this is object two, or something, right? There's just the notion of these things belong together. In some sense, this is a graph. So maybe I have a justification of presenting this 3D group after all.
No, that's the point of the that we need to rename the reading group because most of the time we don't talk about graph and geometry related papers.
I would say this is a set of sets, or maybe just a collection of sets, and that's the right notion, right? Because each object is really a set of tokens, and within the set there's no notion of order.
Yeah.
And transformers are really good at representing sets, and with this hierarchical attention, they're good at representing sets of sets.
Yeah.
I guess
Well,
that.
you could have like some row form or some rotary positional, like some relative positional encoding via row former stuff to tell the objects apart without imposing an order.
Yeah, that is an interesting idea, but then you still have a notion of distance, right? Because even though there's no absolute position, you're totally right about that, but there's still objects one and two are closer than objects one and three with the rotary positional embedding.
Yeah, I'm sure you can fudge around with the positional encoding somehow to get it to work, such that the bias just contains it's the same or not the same object, but yeah, doesn't really matter.
Yeah, I think that would be interesting. But yeah, in the end, that's exactly what we wanted to achieve with this attention thing. Um, and I mean, I don't really have a good. We never compared to something like rotary positional embeddings because it felt like it had the wrong symmetries.
Anyway, it's kind of beside the point of what we don't want a good architecture for this task now. We want to compare
Yes,
stuff.
yes, and we try to be fair in this. Of course, we it's hard to be entirely fair because at the bottom of your heart, maybe you do wish for the equivariant thing to be better. But what I can say is that we spent more time on the baseline transformer and getting that to work well than on the equivariant one. Okay, so that's what I wanted to say about the models. I think the more interesting part of this is how we studied the scaling. And what we wanted to do is a three-dimensional scaling study. So what you see here on the right-hand side, the three axes we wanted to analyze is the amount of training data. Maybe I can get a laser pointer.
Sorry, you just said this thing at the bottom of our heart. Maybe we want the equivariant architecture to work better. And like, yeah, in some sense, I would find it nice and or it just makes sense, right? Or it is easier to understand. But for practical purposes, and if I'm now implementing my large scale models, it is really nice not to have to care about equivariance and basically be freed from this restriction, and I can just do whatever I want and try out whatever I want without having to always think about this additional constraint.
Yes, I actually wholeheartedly agree with that. I'm now at a startup, and there is kind of much more about what can you get to work with the limited amount of time, and then suddenly equivariance doesn't look so tempting anymore. If you're really, I think I wanted to say this at the end, but I can already maybe say it now. If you are kind of limited by engineering hours, then equivariance is not such an attractive proposition. If you're limited by compute hours, who knows? We get to that.
Okay.
Yes, so to study the scaling, what we really wanted to do is study three dimensions. So the amount of training data, length of training, and the size of your model. And the length of training and the size of your model together determine the total amount of training compute you have. And the size of the model also determines the total amount of test time compute you have, but we didn't really look into that. In a perfect world, we would have been able to fit one scaling law to all three axes simultaneously, but we weren't able to do that. And I don't really know why. We tried some of the data scaling laws that were proposed, so data and compute scaling laws that were proposed in the literature. They just didn't describe our data well. So what we ended up doing is separate these two aspects. We have a kind of separate study of scaling with amount of training data, where we fix the other two aspects, and then we kind of fix the data to basically be infinite and study the scaling with compute. What we do for the data scaling study is really just pick one model size, and we use the model size that worked as well as possible for that amount of compute, and one training duration, and then vary the amount of training data you have. And of course, you have to be a bit careful with things like overfitting, but basically, that's it. So as you go to smaller and smaller training data sets, you of course increase the number of epochs. We start in the one epoch limit, and we go to I don't know, many epochs. And we were not able to find a nice scaling law for this, so we analyzed this mostly quantitatively, and I get to the results later. For the compute scaling, we followed the standard approach that people have been following in language and also in vision papers. So here we want to study the scaling with both the model size and the training length. And what we do is that we perform a number of experiments for different combinations of these two factors. So these are the dots on this figure. And we keep the training data fixed, so basically be infinite. It's, I think for some of the data points, maybe we have a couple, like order of 2 or 3 or so epochs, because we couldn't really afford to generate that much training data, but still, it's essentially infinite for this study. Step 2 is that you then take all this data you collected, all these experiments, look at the test laws you have for them, and fit scaling law ansatz to that. And we used the same ansatz that was popularized by the Kaplan and Hoffman papers. Hoffman is the chinchilla paper. Maybe you've seen that for language modeling. So this is a power law in the number of parameters and in the length of the training. And there's also an offset parameter, but we found through cross-validation that we could set that to 0 and get a better performance of the fit. Okay, but you don't really just care about the loss as a function of model size and training. What you really want is the loss as a function of your compute budget. So to get to this, you first have to quantify your compute budgets. And again, following language modeling approaches, we counted the number of flops during training, so floating point operations. And in some approximations, if your models are big enough and if your data is big enough, this is proportional to the product of the model parameters and the number of training steps, or more precise, the number of tokens seen during training. And there's a prefactor for this proportionality, and this depends on the model. For standard transformers, it's quite infamously, this prefactor is 6, and you can more or less derive this. And this counts both the forward and backward passes during training. And for our equivariant architectures, we could also count this factor, and it depends a little bit on hyperparameters, how much of these geometric algebra representations you use and how much of the kind of standard scalar representations you use. For the hyperparameters we used for us that we found to be optimal, we found something like 6t, 60. So this is as expected. If you have the same number of parameters, an equivariant architecture performs more compute than a non-equivariant architecture, right? 60 is a bigger proportionality factor than 6. Step 4 in this approach is after you fit your scaling law, your power law as a function of n and d, and you have the relation between training compute and n and d.
Johann,
Yes?
why are we doing all the scaling law stuff instead of just looking at the numbers that we get out when training at a certain budget and looking at the performance for all the numbers along these parameters?
Yeah, okay, that is a great question. I think the canonical answer is that people have previously found that the scaling laws often extrapolate. So you could predict how the performance would change even for a couple of orders of magnitude beyond where you performed your experiments. And this worked remarkably well in language modeling, a little bit less well in vision. But I will not be able to show you that this is the case in this experiment.
Yeah, okay.
So if you want, you can also just look at the data points. I have them on the slides as well. There's, of course, more points than lines. So maybe the lines are a little bit easier to see.
Yeah, yeah. Whatever you think is the most useful.
Yeah. But I do think it's, um, yeah, okay. I think I don't really, don't want to speculate too much, but I think it would be very nice to check if these scaling laws do extrapolate, if you can really use them to predict the performance a few orders of magnitudes beyond where you did your experiments. But we didn't have the computer to do that, sadly.
Yeah.
But yeah, just to finish how you would do this, if you do care about scaling laws, you can derive kind of the optimal allocation of a given compute budget on the number of parameters and then the amount of data you have. And then finally plug this into your scaling law again, into your test loss as a function of n and d, and get the scaling with compute. So then the best possible loss you can achieve with the model as a function of the compute you have. And it turns out miraculously that this is also a power law in the compute with a different exponent. And this exponent is, of course, related to all the other factors you found in your study. Okay. That is what we did. And before I get to any results, I want to make one thing really clear, that our study is quite limited in a number of ways. I wish I could really answer the question of whether equivariance matters at scale, but first, of course, we only study one benchmark and we only compare two architectures. There's no chemistry in our study. There's not even a kind of, I don't know, astrophysics experiment or something. There's no message passing neural network. So it's really just a small subset of the big space of questions you could ask. We put some computational effort into this, and we performed a number of experiments, and we go to something like 10 exaflops. And I think that wasn't so bad, but this is still quite a bit smaller than what current language models have. So I think Llama 3.1 was trained for 10 to the 25 flops or so. So that's just insanely much more. And unfortunately, we couldn't afford that. We do not look at a test time compute, just training time compute. So I think that will also be something to discuss. And I think maybe the most important thing in here is we count these flops really by more or less counting flops, kind of looking at what are the number of floating point operations that matrix multiplications require during the forward and backward pass, and looking at the appropriate limits for scaling and so on, similar to how people do it in language modeling. But the actual wall time depends on many more things, in particular on the implementation of your network architecture. And I can give you a quick idea of how much this varies with this plot. So what you have here is on the x-axis, the number of parameters of models we trained. On the y-axis, the throughput of these counted flops we had. So the number of these nominal theoretic flops that we found per second of wall time. You have to be a bit careful. This is not an apples to apples comparison, because we have some experiments where we used a single GPU. These were A100s. And we have some experiments where we used a variable number of GPUs, but because of cluster limitations, sometimes we use them with 2 GPUs, sometimes with 8, and sometimes with something in between. So it's really not very scientific. We didn't plan to make this plot. It was just a after the fact thing. What you see here is, first of all, that the throughput really varies over 2 orders of magnitude. So this is quite extreme. And the main driving factor is GPU utilization. If you can use bigger models or bigger batch sizes, we didn't really optimize batch sizes here at all, you can get a much higher throughput. And second, there is a gap between the standard transformer and equivariant architectures. If you look at this, there's quite a big factor between the two. But this is a statement about implementations. And for instance, maybe you've seen that NVIDIA, and in particular Mario Geiger, recently released NVIDIA-optimized implementation of Maze, which turned out to be much more efficient than the original Maze implementation by, I think, in some experiments, a factor of 10 or so. So I really think that this is something that one could change. But right now, equivariant architectures are much less optimized than non-equivariant architectures. And that's maybe even a very general statement.
Okay, Johann, like the model size is now in terms of parameters.
Yes.
Okay, the thing that I kind of want to understand is how basically the RAM that's used up on my GPU compared to performance.
Mm.
So how do I have to translate this into RAM, right? Because that's what I'll be limited by. I'll have one sample per GPU. I'll have maybe 128 GPUs, and then my model, I either need to introduce like lots of checkpointing or so, or maybe even that even doesn't help. And um, yeah, and then yeah, how like if I train with my transformer, then how much RAM do those operations use up compared um to your SE3 equivalent transformer?
Um, we didn't study this in this paper, but if you give me 10 seconds, let me pull up a plot that's looked at exactly that in a previous paper.
Okay, then I'll distract the audience while you pull
Yes,
up.
please do a trick or something. This hopefully shouldn't take too long.
And then while by to distract the audience, I will show a sun, which recently was stitched together for me as a present by Rachel Wu, because I always call people friends of the sun, including the people in the reading group. So I call you the friends of the sun. So I guess you're now all friends of this little plushie. Um, yeah, which I first thought was an octopus, but it's a sun. Okay,
Why
sorry,
can
this
I?
is maybe not the best distraction, but a more interesting distraction would be, ah, but then we no longer need distractions.
No,
Okay,
sorry, you just said more interesting distraction. But
um, that would have been like the question of, yeah, why do people like AlphaFolds and so on now use non-equivariant architectures? And yeah, you said one thing of the engineering time or engineering efficiency, and but yeah, then maybe another thing is just that it is also easier to fit the same architecture in um, or yeah, the easier to fit an architecture of the same size and capacity within the class that we actually care about. So let's say within the equivariant class into into memory, literally, with a non-equivariant architecture than with an equivariant architecture.
yeah, and yeah, I think that that is a fair point. So what we saw here, this is the paper where we worked out the equivariant transformer that I'm now talking about. And what we have here at the top is a comparison of a transformer versus an equivariant transformer. So now you have to totally switch context because now the non-equivariant transformer is red and the equivariant transformer is green. I'm sorry for this. Um, and at the top panel here, you see the GPU memory usage, peak memory usage during, I think, forward and backward passes as a now not as a function of the compute budget, but as a function of the sequence length you have in your problem, because um, that can be a big factor. And don't look at these message passing neural networks up here. That's maybe not entirely relevant to this point, but these two lines, what we do see here is that um, they're kind of in the same order of magnitude within a factor of two. And the reason for this is that they both use the same flash attention backend, which, if you have long enough sequence length, actually for, yeah, is that the memory bottleneck actually? I'm not sure. Yeah, but it really depends then how many channels you need, relatively speaking, because you need smaller representations when you use equivariant representations. You need less channels than if you use
Yeah.
non-equivariant ones. So there is even the chance to save some memory, but of course the operations, especially the backward pass, will take more memory. Um, what we found a smaller difference in terms of memory than in terms of wall time in compute. So what we saw here is if you have small problems, so kind of lower GPU utilization, the equivariant architecture is really an order of magnitude less wall time efficient than the non-equivariant one. That was the biggest downside we found, and memory was not as big of a problem. But yeah, it will depend on so many factors that I don't really want to say something too strong here. But it was not the fact that the equivariant architecture was much more memory hungry. I think that I can say confidently.
Okay, if anyone has some good time on their hands, then please take the Boltz repository, which has training code for AlphaFold. Boltz is a AlphaFold 3 clone, has training code available. Just replace the diffusion module transformer with this scatter or with geometric algebra transformer, right? And see what happens. And yeah, the evaluation should be everything, all the evaluations are also implemented in this open source repo. So there should be just switching out this transformer for the diffusion module.
That'll be very fun.
Yeah.
Um, yes, and I have nothing more to say here. But let me tell you what we found in our paper. You see my screen again?
Yeah.
Good. I think we have kind of evidence in our results for four very careful conclusions. And please keep these limitations in mind that I really don't want to oversell this. The first one is not very surprising. If you've been active in this field of geometric deep learning, the one benefit that everybody tells you about for equivariant architecture is if you have very little data with equivariant architectures, you learn all the symmetry transformed data at once, so they should be more data efficient. And that's also what we find. So this red line here shows the loss that we achieve with the equivariant architecture compared to this blue line for the non-equivariant architecture. And if we go to the left side in this plot, which is small number of training data set, keeping the overall training length constant, so many epochs on small training data set, there's a big gap in performance. But if you train for many epochs with data augmentation from the symmetry group, which is this cyan line, you basically get the same thing. And that's interesting. I think the conclusion from this is that data efficiency alone, if you have infinite compute, isn't really an argument. Because then you could just use your infinite compute to train with data augmentation for a long time. And at least in our experiment, we found the same performance. It just takes a lot of epochs. And we think we
What am I missing here? Like data augmentation here does not achieve the same loss as the equivariant model, right?
it does in the sorry, this is a bit confusing. Maybe we should have formatted it differently. So in the left side of this plot, it does. They're the same here. And this is the region where the number of epochs is large. Sorry, let me say this first. What this plot shows on the x-axis is the number of tokens we have in the training data set. And what we keep constant during these experiments is the training length.
So you think if we were to put up the number of epochs very high,
yes,
then the blue and red, sorry, the light blue and red would be the same.
that's right, yes.
Got it.
But we didn't have like this already took weeks on the number of GPUs, and we didn't have the time to do this times 100, or I guess you'd even need much more than times 100. Yeah.
Yeah.
So the only way where we could study this is by making the training data set small and then doing many epochs. And then we saw the same performance for the two. So what you should think of this when you see this plot is kind of the left side is many epochs and the right side is few epochs. And with many epochs, augmentation and equivariant architecture perform the same for us. So the second finding we have, and now we're coming to compute efficiency, is first of all, if you look at the scaling with compute, then the scaling laws actually fit the data reasonably well. Not perfectly well. There's some outlier data points, but still overall not bad. So what you see here is 4 panels. Each panel has a different training compute budget, so different number of overall flops used to train these models. And the x-axis in each panel varies the trade-off between the model parameters and the training length. So each point is one experiment with a different model size. The red models are equivariant, the blue models are non-equivariant, but within each panel, they have the same compute budget. And then the y-axis is the loss. And the lines show you what this power law that I showed you earlier predicts when fitted to all this data.
Are
And
all the losses training or test losses?
Test loss, always. And it's not a perfect fit, right? You see some like this one is a weird guy, and I guess this is maybe a bit more stochastic because we have a big model and little flops, so it's trained for just a short amount of time. Also these points. But overall, I think we can say this is a pretty reasonable fit. And also, if you look at, we have some way of dealing with uncertainties, basically through, I'm lacking on the word, doesn't really matter. But we find that kind of most of the data points lie within the 95% confidence interval that we're showing as well. So that's reassuring. But I think that the most interesting thing is not this plot, but if you kind of now for each flop budget, find the best possible performance you can get for each of these models, and then look at the optimal performance as a function of compute you can get. And what we find there is maybe a little bit more surprising than what we saw so far. And what we find is that equivariant models are also more compute efficient. So what you see in this plot on the x-axis is the amount of training compute measured in flops. And what we see on the y-axis is the test lots. And all the dots are the different experiments. Some of them are kind of at optimal configurations for a given flop budget. Some of them are kind of way too big models and trained for too short, or the other way around. And the line shows you the fit we have from the scaling laws. But you can also just look at kind of the lowest point you have at each budget. And you find that at each compute budget we looked at, the best equivariant models are better than the best non-equivariant models by not quite by the same constant factor, but roughly by a constant factor. And this is all in the infinite data limit. So this has nothing to do with data efficiency. The way that I would think about this is you can absolutely learn symmetries from data, but that costs you flops. And if you already start from equivariant functions, you can use the flops that you have to really narrow down on your class of functions further and get a more precise result. And again, please keep the caveat in mind that this is all these kind of counted flops and not wall time. And if you look at wall time in our practical experiments with our implementations, the difference is much smaller. And the final thing we found, if we look at the optimal allocation, optimal model size and optimal training is given a training budget, that there are different trade-offs for transformers and, equivariant and non-equivariant transformers. And we don't really have a great explanation for this. So what you see here is the optimal number of model parameters as a function of the compute budget. And if we have kind of small compute budgets, then the best equivariant architecture is actually tiny. So the strong inductive bias of these architectures carries quite a lot. You don't need many parameters. A transformer needs to be quite a bit bigger, but this gap narrows down quite a bit later. So yeah, we have some speculation about this in the paper, but it's quite technical, and maybe it's also specific to these architectures that don't really have a good, satisfying story behind this. I think there are two things I personally took away from this work, and maybe this is something that you find interesting as well. The first is, usually people talk about data efficiency when they talk about equivariant architectures, right? Like equivariance helps you when you have little data. And I think it could make sense to shift the focus a little bit and talk more about compute efficiency. Because if you have little data but lots of compute, you can just data augment away and you'll be happy. But if you're limited in compute at some point, equivariance can still buy you something because it kind of saves you from learning symmetries from data. So compute efficiency is really maybe the secret power of equivariant architectures. In practice, however, the problem is that we're not really unlocking that compute efficiency because we see a lower, less flops per actual wall time for equivariant architectures. And of course, this is most likely our fault because we used our own equivariant architectures with this not ideal implementation. But maybe I can be so bold and to say that the whole community would benefit from investing more into making the implementations of equivariant architectures more efficient in the sense of having a higher throughput of flops per wall time. And if we do that, we may get to the point where the compute efficiency benefits of equivariance actually translate into, it's easier in the real world to achieve good performance with equivariant architectures, because I don't think we are at that point right now. That's all I wanted to say about this paper. This was work together with my colleagues at Qualcomm, Sönke, Pim, and Taco. And obligatory plug, if you found this interesting, please have a look at our paper on the archive. And I hope you still have a couple of questions.
Very nice. And I find it very pleasurable that you say things like you do not want to oversell the results, and you do indeed not oversell them. Um, that may not be a given, and some other papers may not do the same. Maybe also other papers on the other side of this debate. They're trying to sell a lot, but I know the two papers that, or the three papers that you mentioned that use non-equivariant architectures. I know AlphaFold, I know this molecular conformer fields thing,
Mhm.
but I don't know ORB. Can you
Mhm.
can you tell us a little bit about that? Like just how I say AlphaFold 3 is the state-of-the-art model for protein structure prediction, which is the task of taking the sequence of a protein as input and then predicting the 3D structure that the sequence folds up into. What is this other paper doing?
Yes, let me, do you see the website? Yes, I hope so.
Or
So maybe you're aware of interatomic potentials on machine learning force fields. So
yeah.
the problem is you have a bunch of atoms, 3D positions plus elements, and the task is to predict the energies and the forces acting on each atom. And this was one of the fields where until a year ago, basically all of the state-of-the-art methods were equivariant architecture. So there's Maze is a very popular one. There is Equiformer developed by, well, some people at Meta and some people at some universities, and probably, yeah, I will not.
From MIT with Tess Smith.
Yes, exactly. Thanks.
Yeah, but
Um,
now anyway, what is the and it's this thing is now better, I suppose. But
no.
okay, good.
That depends. I think so. My very short take on this, and I probably not doing anybody justice, is that ORB is pretty good if you look at mean absolute errors in benchmarks, but it's not like clearly better or so than others. Like there's
Mean energy errors or what?
a mean absolute errors both on energies and forces. It's pretty good. I would say it's one of the best that we have right now. But maybe because of the lack of strong inductive biases, maybe equivariance, but maybe more importantly, because it doesn't model forces as a gradient of the energy. It really just directly predicts forces. So it's not conservative, is the physics word for that. It is, some people found that it doesn't really work so well for the usual applications that you use these force fields for, which is not really finding a low error on forces in some benchmark, but it's more about taking a molecular structure and optimizing the geometry of that.
Well, wait a second. How do these people construct their training test split? Do they train, like I've seen some papers that train with the same molecules as they evaluate on, but they like take just different 3D structures for these.
I don't know that. That's a good question.
Uh,
I think for
uh,
these benchmarks, usually there's some limitations on what you can train on. So I hope that's fair. There's
yeah,
you probably know this better than I do, but there's this MatBench discovery thing. And if you look at the current um, list of best things, it looks like ORB is in second place, but I don't really know what went into this. Yeah.
yeah. I guess yeah, lots of questions also about force fields and
Yeah.
like what sort of data this is now trained on. Is this now also for materials or is
Yeah.
this for MD simulations of biomolecules or small molecules? Yeah, not
So the startup is in materials design, and they trained mostly on the materials project data. Maybe they have some other stuff. I'm sure they have in-house data as well, but the public version, I think, was trained on materials project.
then for these things, I think if you can just predict energies and right, okay, but no, they still use the predicted forces for simulation and don't predict energies, you said. Yeah, anyway,
So they still
good.
predict energies, but there's no direct link between the energy predictions and the force predictions. So other models usually take the gradient of the energies to get the forces, and they don't do that.
But you can still do that, just not
Yeah.
what they. Yeah.
But then you
Anyway,
don't know if the forces, like it has never done that during training, so maybe the forces are not very good. But I haven't looked into that.
so one point I wanted to get in and quickly also still talk about regarding the equivariance question is, right? We now had the question of so in principle it is clearly better if you have a model whose class of functions already captures like the function that you want to model in the end, if you know what function you want to model in the end. And but then there are caveats of if you then have that model, is it slower to train? If you have that model, is it larger and will need more batch size? And but then the third thing would be um, like does one iteration take longer? Is the one question. Like does just running the model take longer? Or like a third question is for is optimization of this model class harder? And gradient descent is worse at finding a well generalizing minimum of its loss landscape.
Yes.
Yeah, that's maybe something we haven't really discussed much.
Yes, no, I agree with all of this. And in principle, most of these aspects contributed to the numbers we found in the end, right?
Yeah,
But
yeah.
we don't have the ability to distinguish between if something is an optimization effect or, uh, you know,
Right. Your numbers do contain this information. We just cannot disentangle between all three of them and um or between the two of them, let's say that.
mm,
And yeah, I just wanted to bring it up as like
yeah,
having in mind that this also contributes to the time that you take until you achieve a certain loss.
yes, I agree.
But then we have Ravi with a question or a raised hand.
Hi, I'm Johann and Hans. Thank you for thank you. I can go ahead and ask my question now, or
Yeah, please.
yeah, thank you, Hans. Johann, thank you for the presentation. I really appreciate it. I really liked your presentation. I just wanted to ask a question about how you arrived at at your takeaway that equivalent models are data efficient, compute efficient. Can you go back to your can you go back to your slides if possible?
Oh, of course, I think.
So what's the question? What was the conclusion that you're asking about?
Yeah, I just wanted to ask about the factors that he took into account when he came to when he came to the conclusion that equivariant models are data efficient, compute efficient. I mean, I saw the model parameters were taken into account. I just wanted to ask if were there any other factors that you, Johan, took into account, or if it was already mentioned, please forgive me for
Oh,
that.
no worries.
No, of course. So with data efficiency, I have to say we put less effort into this than the other thing because the computer efficiency I thought was a bit more interesting. But this is basically the plot you see on the right-hand side here. So on the,
Nope, nope, we don't see anything.
oh, you don't see anything. That is a shame.
Uh,
But
now
now,
we do.
good.
Oh, but
So what you see here is kind of one setting for the model size and how long we train the model for, and then we just change the amount of data that we have. And if we start at the right side, you have kind of infinite data, and when you go to the left side, you have less and less training data. So kind of pushing you to less and less data and more epochs. And the red line shows you how the loss of the equivariant model gets worse, and the blue line shows you how the loss of the non-equivariant model gets worse. And you see that in the beginning, this gap is entirely due to compute efficiency because we're training on essentially infinite data, a single epoch. But then when we limit the amount of training data and go to the left, the equivariant model gets worse, of course, but the non-equivariant model gets much worse. So the gap widens. And that's the reason why I say that equivariant models are more data efficient. Again, this is only true if you don't look at data augmentation from the symmetry group. And we found that then actually training for many epochs can really close this gap. So this is I don't want to highlight this data efficiency. I think the interesting thing is that we see benefits for compute efficiency. And the benefits for compute efficiency, I think, are best summarized in this plot. So this is kind of infinite data setting. And the x-axis is the amount of compute you have. And the blue and red line are a summary of the performance of the non-equivariant and the equivariant model. And we see that kind of the equivariant model at each compute budget is roughly a factor of, what is this, 2 point something better in loss than the non-equivariant model. This distance stays the same. It is not that if you have enough compute at some point, the transformer, the non-equivariant transformer, is equally good. They maintain the advantage. Maybe they would cross at some point or be equal, but we haven't gotten to that point. Did that make sense?
It does make sense. It does make sense. Thank you so much, Johann.
Of course.
Righties, then in the chat we also have someone asking, have you looked at eigenvalues, sharpness, and so on to analyze the loss landscape? My guess is no. Interrupt me if that's wrong. And they are also asking, and would you think that maybe because non-equivariant architectures might have better properties in this regard, they would achieve lower loss than equivariant models if we had infinite data and infinite compute?
We've not done that. You are totally correct in your assumption. There is a recent paper by Andrew Wilson's lab on this question that maybe you've seen, and I can't recall the title of it, but I think you'd find it through Andrew Wilson's Twitter or Blue Sky or so.
Andrew Wilson.
Yes.
Andrew Gordon Wilson.
Yes, exactly.
All right. Okay. Yeah. Is it the one with they have these different matrices for structured matrices?
I think that was, I mean, he also did that, but I'm not sure if it was this paper.
Different.
I think it may have been a different paper.
But then while you're searching, Nesta, to your second question, and would you think that maybe because non-equivariant architectures might have better properties in this regard, they would achieve lower loss than equivariant models if we had infinite data and infinite compute? No, if we have infinite data and infinite well, yes, if we have infinite data and infinite compute, we can, with the more expressive architecture, always try every possibility of parameter combinations and find something that achieves lower loss on your training data. But then probably if you have infinite compute, then trying every parameter of your equivariant model will give you a better solution because you're just respecting one additional symmetry. But that's not the point of optimization, right? This goes against the point of optimization being hard. And like if optimization, or if you had infinite compute, then you wouldn't care about whether or not optimization is hard. Johann, do you think you wanna do you have the paper or anything?
No, I'm not finding it. I'm not even sure. I think it was Wilson, but I'm not even sure about it now.
Are there any scenarios where equivariant models have an advantage over data augmentation for data efficiency?
I want to say one thing that I didn't mention earlier. Everything I've said so far was only really on pretty small symmetry groups, right? Like global E3 is a small symmetry group. It's okay, it's infinitely big, but it only has 6 generators. There are problems where the symmetry group grows with the size of your data, with the size of your problem. For instance, in some quantum mechanical problems, you have not something like E3 or maybe O3, but more like O3 to the power of n, where n is the number of particles you have.
Yeah.
These are called gauge symmetries. And in this case, you always win with equivariance, no matter if you look at data efficiency or compute efficiency, because it's just such a gigantic difference in what you have to learn.
Yeah.
So I think maybe that partially answers that question.
Okay, but then I would call the day here for, let's say, the official part or whatever goes in the recording, and finish that with your last words if you have any additional last words that you want to say.
No last words. Thank you very much for having me.